Hi everyone. Today we are going to learn how to predict the products of both synthesis and decomposition reactions. There is a set of rules that we will use to help us learn how to predict the products of both of these reaction types. There are actually 5 rules for predicting these, but the 5th rule is a little bit complicated for our level, and so we will just work with 4 rules. Okay, so the way that I'm going to do this is I will use these 2 workbook pages from the workbook, so synthesis, reaction rules and practice, and then decomp. And I'll just kind of keep switching back and forth between the 2. So if you want to have both of those out in front of you, that will help. And we'll just keep switching back and forth, meaning I will teach rule number 1 for synthesis, and then I'll go and teach rule number 1 for decomp. Remember, any synthesis reaction is essentially the forward reaction, and decomposition would be the reverse. Here's what I mean by that. We could say Na plus Cl2 yields NaCl. This is not balanced. And this would be the synthesis reaction. And then I could do this in reverse. So NaCl decomposes into Na plus Cl2, again, not balanced. But these reactions are essentially opposites of one another. Okay, so I will teach the rules to you kind of in that same manner. All right, let's get started. So rule number 1 for synthesis says the direct union of 2 elements will produce a binary compound. This is the most simplistic rule. Essentially, we are just taking 2 elements and sticking them together on the other side of the arrow. Now, remember, just like with single replacement and double replacement reactions, the arrow or the yield sign always acts as a reset button for cross and drop. So we need to recross and drop all of our charges on the other side of the arrow. All right, so the direct union of 2 elements will produce a binary compound. The word binary just means 2 parts, so we take the 2 elements and stick them together to form a binary compound. Let me show you how this looks with an example. So if we go down here, number 2 is this rule that we just learned. So let's look at it. So we have 2 elements here. We have silver, we have oxygen. Your Hofbrinkels are important for this type of reaction. So maybe write yourself a note, Hofbrinkel, just so you don't forget. This is why it is O2 and not just O. Okay, oxygen can't stand alone. However, silver can. Okay, so silver doesn't need that subscript of 2. It can stand alone. All right. All we're going to do with this on the other side of the arrow is recross and drop. So remember, silver has a +1 charge. It is a transition metal that does not change. Its charge is always 1+, and then oxygen is 2-. So we would cross and drop this. Okay, let me erase and then we'll rewrite this. And so our product is Ag2O. Now, all of these would need to be balanced, so we would balance this by putting a 4 here and a 2 here. I'm not going to go into, whoops, what did I just hit? Not going to go into how to balance. I cover that in a different video, and hopefully by now you feel comfortable with balancing. Okay, let's look at another one. So number 9 is also rule number 1. So we have calcium and chlorine. And we are just going to smush them together on the other side of the arrow, making sure to recross and drop. So calcium has a 2+ charge, chlorine a -1. So we end up with CaCl2 like this. And then we would need to balance it. And if we look at this closely, it is already balanced. So we are good to go. Now let's flip over to decomp, because this is the exact same rule, just backward. So here we have the binary compound. So we have the big compound is going to break down into its parts. We also need to remember Hofbrinkels for this side. So I'll just write it right here. Oops. There we go. Okay. For this side, let's see. So number 2, again, is this reaction. So we have silver oxide. and it's going to break down into its parts. So this would yield silver, which can stand alone. So we just leave it just like that. Okay, plus oxygen, which, oops, let me put in a little line. I'm going to erase these. Let me put in a line for balancing. Okay, let me start over. Silver, there we go, plus oxygen. Now remember, oxygen is a Hofbrinkel. It cannot stand alone, so we need to put a 2 here. And then we would need to balance this with a 2 and a 4, like so. Okay, let's look through this. Oh, number 10 is rule number 1. Okay, so let's see how this goes. We have a radium chloride here. This is going to break down into its parts. And so we are going to end up with radium. Radium can stand alone, so just there by itself. And chlorine, which cannot stand alone, so we'll say Cl2. This one is also balanced from the get-go. All right, that is most certainly the easiest rule. Okay, and so let's move on to rule 2 for both synthesis and decomp. In this rule, it says metal oxides plus carbon dioxide react to produce a carbonate. Okay, let's break this down a little bit. But remember, a synthesis reaction isn't always just an element plus an element makes a compound. It could be a smaller compound plus perhaps an element, or a smaller compound plus a smaller compound makes a larger compound. So in general, synthesis reactions are something small plus something small makes something larger. All right, so rule number 2, it says we are first going to combine our first reactant is going to be a metal oxide. So think about what that might mean. A metal, anything with a positive charge on the left side of the table, plus oxygen. Okay, so what are some metal oxides? Well, we could have like MgO. We could have Na2O. These are all metal oxides, right? We could have a transition metal, so we could have like CuO, okay, or Fe2O3. These are all options for metal oxides, all right? So we will have a metal oxide plus carbon dioxide being the other reactant. Then they are going to react to produce a carbonate. Now, when we think about carbonates, we know the formula is CO3, 2 minus. Okay, so our product, it's on this side of the arrow, the anion of our product is going to be a carbonate. We need to get a cation to this carbonate, and so the way that this works is the metal in our metal oxide becomes the cation to our carbonate. I'll show you this through several examples. It's a little easier to understand when we're working with real things. So let's take a look down here. All right, number 4. My synthesis. Oh, there we go. Hang on a second. Let me get to the right. Not number 4. I was on the wrong key. Let's take a look. Here we go. Number 5. All right, so we know that this rule says we have a metal oxide. So where's my pointer? There we go. We have barium oxide. That is a metal and an oxygen, so a metal oxide. And carbon dioxide is going to react to form a carbonate, but carbonate is just the anion. So we know that barium is going to be the cation to our anion, which is carbonate. Barium's charge is 2 plus. Carbonate's charge 2 minus, so we're going to end up with BaCO3 as our product on this side. Okay, I'll erase this little guy. There we go. We would obviously need to check to see that this is balanced, and when I look at it, it is. So 1, 1, 1, and 1, this is already balanced. All right, just to reiterate what happened, so we had a metal oxide and carbon dioxide. The metal of our oxide becomes the cation to our carbonate. Okay, let's try another one. So here we have beryllium oxide, a metal oxide, and carbon dioxide is going to react to form a carbonate. Carbonate is our anion, and that means beryllium is our anion. Oh, what did I just say? Did I say the same thing twice? Carbonate is our anion, and beryllium is our cation. There we go. Got that one right. All right. let's think about charges, because remember, our arrow is a reset button. Everything needs to get recrossed and dropped. Beryllium's charge is 2 plus, carbonate's charge is 2 minus. Those would cancel, and we would end up with BeCO3 as our product. Look here, and we notice this is all balanced. 1 beryllium, 1 carbon, and 1, 2, 3 oxygens and 3 oxygens here. So we are all balanced. All right, let's go back to decomp, because remember, this rule is going to be very similar, just backwards. So now we're starting with the carbonate, that is our reactant, and it will break down into a metal oxide and carbon dioxide. Now, whatever is bonded to our carbonate as the cation will become the metal in our metal oxide. So let's take a peek at how that works. All right, here's one right here, number 6. So we have cesium, carbonate. So we are starting with this one with carbonates, right? So this is going to break down into a metal oxide. Cesium is going to be the metal of our metal oxide. And then we would have carbon dioxide. So let's write our little balancing line. Cesium's charge is 1 plus. Oxygen's charge is 2 minus. So when I cross and drop, this is what my metal oxide looks like, plus carbon dioxide. Okay. So let's reiterate what we did here. Let me erase. First, for balancing, this is 1, 1, 1, and 1. This is already balanced. Okay, so again, carbonates, right here, there we go, break down into metal oxides and carbon dioxide. And the cation of our carbonate becomes the cation of our metal oxide. Just like here, the cation of our metal oxide became the cation of our carbonate. It's backwards. Okay, let's do one more of these. So if we look at number 5, we have barium carbonate here. This is going to break down into a metal oxide, our metal being barium. Barium's charge is 2 plus, carbonate's charge 2 minus. So we have, oh, except for I'm doing oxygen, not carbonate. Starting over. There we go. Barium's charge is 2 plus and oxygen's charge is 2 minus. There we go. Miss Sutton is on board now. Plus carbon dioxide. Okay. If we look 1, 1, 1, and 1, this is already balanced. So that is rule 2. Okay. Let's look at it with synthesis first. So metal oxides plus carbon dioxide react to form carbonates, and carbonates break down to metal oxides plus carbon dioxide. All right, great. Let's go on to rule 3. In rule 3, we have some new vocabulary. We have something called a binary salt. Okay. A binary salt is just a general term that we usually use to reference anything ionic. However, in this case, it's going to be something bonded to chlorine. I will tell you how I know that in just a second. Let's read through the whole thing. So we have a binary salt, which just means we would have some sort of metal with a positive charge bonded to chlorine. Okay. And then our other reactant is oxygen. Remember, oxygen is a Hofbrinkel. This is going to react to produce a chlorate. All right. So as a reminder, chlorate's charge is ClO3, 1 minus. And then let's see. So over on this side, I knew I have a binary salt. That's going to be some metal bonded to chlorine plus oxygen gas. This is our rule, right? So binary salts plus oxygen. Now, the reason I knew in my binary salt that the anion was chlorine is because over here I have chlorate. I need the chlorine to come from somewhere, and this is where it's coming from. Okay, now just, oops, I guess we're erasing it all. Let me write my chlorate again. Just like with the rule we just learned where we produced a carbonate, right? And the cation to our carbonate was the metal, the same thing applies here. Whatever our chlorine is bonded to becomes the cation to our chlorate. Okay, so we know that it's going to be a metal plus chlorine. That's our binary salt. We know it's chlorine because we have chlorate. Oxygen is our other reactant. Okay, and whatever we have here has to bond with the chlorate on this side as the cation. Remember, all of these, and I should have said this at the beginning, all of these satisfy the law of conservation of matter. We can't just have elements disappearing. So if I have something over here, it has to also be represented over here. Just like I have this here and I'm representing that here. And this here is representing this here. Okay, so whatever elements we have on the reactant side, we also have to have on the product side. Let's take a peek down below. Let me erase all of this. Go down here. All right, let's find some that satisfy this rule. So again, we need to have a binary salt, but our binary salt is always going to end in chlorine. Okay, plus oxygen yields a chlorate. And then magnesium will be the cation to our chlorate. So over here, I have magnesium with a 2+ charge. Chlorate is ClO3 1-, and when I cross and drop, this is what I get. And I need to balance this here, so 3 right here. Yep, that works just fine. All right, so now this is balanced. Let's take a look if we have any other examples, and we do. So this one right here. Okay, we have sodium chloride. That is our binary salt, plus oxygen gas, reacts to produce a chlorate. Remember, sodium is going to be the metal of our chlorates. So we have sodium with a +1 charge, ClO3 with a -1 charge. And this is what we end up with. And let me take a peek. This should be 2, this should be a 3, this should be a 2, and then we are all balanced. All right, it looks like we've got one more that satisfies this rule, and that's this guy right down here. So let's see what we can do. We know we have a binary salt and oxygen to produce a chlorate, and potassium is our cation. So potassium has a +1 charge, chlorate ClO3 1-, cross and drop, and we get this. And we would balance this with 2, 3, and 2 again. Erase that. Oops, I want to erase right here. Okay, great. Now, remember, when we go to the decomp side, it's going to be the same thing, but backwards. So now our chlorate is going to break down into, oh, wow. I just made an arrow. I don't know how I did that. Still learning the iPad. Okay, our chlorate is going to break down into our binary salt and oxygen gas. And remember, whatever is bonded to our chlorate becomes the metal in our binary salt, and the anion in our binary salt is always chlorine, so that we satisfy that law of conservation of matter. Okay, let's take a peek down here. Here's a chlorate, number 1. So this is going to break down into a binary salt, nickel being our metal in that binary salt. I can tell nickel is a transition metal, but I can tell its charge is 2 because I can uncross. And so its charge will also be 2 over here. So I have nickel with a 2+ charge, chlorine with a 1- charge, so NiCl2. And my other reactant is oxygen, but oxygen is a Hofbrinkel. It can't stand alone. So we make it a Hofbrinkel like this. And as I look, let's see, 3, 6 oxygens. Yep, we're all good, just like that. All right, let's see if we have any others. So over here, we've got rubidium chlorate. Okay, rubidium chlorate is going to break down into rubidium chloride, both with a +1 and a -1 charge, plus oxygen gas. And we've got a 2 and a 2 and a 3 to balance that. Finally, one more chlorate. This is going to break down into potassium chloride, +1, -1 there, and oxygen gas with a 2, 2, and 3. Gosh, I'm seeing a pattern here. 2, 2, and 3 for our balancing coefficients for here. All right, Let's learn our last rule. That rule says, let me erase my little markings. There we go. This rule says metal oxides again. We know what that is. But now it's plus water. Up here it was plus carbon dioxide. Okay, so a metal oxide plus water is going to react to produce a base. Ooh, new vocab. Remember, a base is anything metal bonded to hydroxide. Okay, so bases end in OH. So it'll be a metal bonded to a hydroxide. Remember, the metal in our metal oxide will be the metal in our metal hydroxide. Let's take a look down here. All right, so here is a metal oxide, and this time plus water. So this is going to react to form a base. The metal of our base is potassium. So we have potassium with a +1 charge, hydroxide with a -1 charge. We are going to form KOH, balanced with a 1, 1, 2. Okay, here's one more. So our metal oxide, aluminum oxide this time, plus water, is going to react to form aluminum hydroxide. Remember, aluminum has a 3+ charge, and hydroxide is a polyatomic. So when what's coming down from the metal is over 1, we need to, or greater than 1, we need to protect our polyatomic in parentheses. So it looks like this. Okay, and our balancing coefficients here are 1, 3, 2. Sorry, I had to think about that one for just 1 second. 1, 3, 2. Yep, now we are all good. All right, last rule, decomp. Exact same thing, just backwards. So our base will break down into a metal oxide plus water. Let's see if we can do an example. Here we have iron 3 hydroxide. I knew that this was iron 3 because I uncrossed, and it will be iron 3 on the other side. So I'm going to end up with Fe2O3 when I make my metal oxide. Remember, oxygen's charge -2. Iron's charge in this case is a 3, and plus water. Okay, and we're going to balance that with a 2, a 1, and a 3. Okay, great. Let's do one more of those. We'll do this one, aluminum hydroxide. We'll break down into a metal oxide, aluminum being the metal. So we have aluminum with a 3+ charge, oxygen with a 2- charge. So this is how we write aluminum oxide plus water. Okay, we'll balance that, 2, 1, 3, and we are all set. All right, guys, I hope this helps you predict the products of synthesis and decomp reactions. Talk to you later.